Well, good morning. This is 11:31, 1 minute late starting getting started on linear algebra class on the 31st of October 2019, which is Halloween. Maybe it's my trick or a treat, I don't know, not much of a treat. But hopefully students will be coming in later, because right now I'm the only one in the room. So let's get started where we left off last time. Oops, let me get the slideshow set up from current slide, blank slide. And where we were last time, right at the top of page 122. Chapter 3 is determinants, and 3.3 is properties of determinants, and we've been looking at a couple of those already. The determinant of a matrix product is the product of their determinants, okay? The determinant of a scalar multiple of a matrix is C raised to the nth for an n by n matrix times the determinant of the matrix A. Now the next one on page 122, top of the page, determinants and the inverse of a matrix, okay? Says here it can be difficult to tell by inspection whether or not a matrix has an inverse. And it asks, can you tell which of the following two matrices is invertible? Let me get my pen set up. Okay, here's matrix A. 0, 2, negative 1. 3, negative 2, 1. And 3, 2, negative 1. Okay, here's matrix B. 0, 2, negative 1. Looks a lot like the other one. 3, negative 2, 1. Just like the other one. And 3, 2, 1. Not quite like the other one. Missing one side. Okay. And it says, can you tell which of the following two matrices is invertible? All right. Now remember, these matrices are not necessarily representing equations, systems of equations, or anything else. They're just two matrices. And all we're interested in now is if they're invertible. Okay, now I hope you recall that if two rows, one row is a multiple of another row, then that's not a invertible matrix, because when you did your row reduction, you're going to have a row of zeros. That would produce a non-remote invertible matrix, because if you're doing that, you know, with the adjoint to a identity matrix, you wind up with a row of zeros. No way that's going to work. But not only can two rows one not be a multiple of another, the same is true with matrices about columns. If two columns are, one column is a multiple of another column, or one row is a multiple of another row, then the determinant of that matrix is going to be 0, and if the determinant is 0, that means it's a non-invertible or a singular matrix. And looking at this one, if you notice, column 2 is exactly a multiple of column 3. Multiply column 3 by a negative 2, and you get column 2. So that means this is not invertible. Okay? Now, looking at matrix B, you can't say for sure whether it's invertible or not, but at least it doesn't have the obvious column or row that's a multiple of another column or row. Now, so you can tell the one is not invertible. It says, can you tell which of the two matrices is invertible? Since A is not, you would have to assume B is, but you can't tell that just by looking at it. Okay? The next theorem shows that the determinants are useful for classifying square matrices as invertible or non-invertible. And it seems like we've already done this, but we'll do it again. And here's what theorem 3.7 says. A square matrix A is invertible if and only if, I like that symbol for if and only if, the determinant of A is not equal to 0. Okay? If the determinant is equal to 0, not invertible. If the determinant is not equal to 0, it is invertible. So, to better answer the question, we could do a row or column reduction of matrix B and see what the determinant is. Now, you could expand it like we do most 3x3s, or it's a pretty easy thing to do the new column 2, let me see. Let me clean this up a little bit. Okay. 2 times column 3 plus column 2 is the new column 2. Okay, so let's do that. That's a legal maneuver. So this would produce, you got a 0, 3, 3 here. Okay, I see another thing we could have done, and that would have been pretty easy too, but this works too. And this would be 2 times column 3 plus column 2 would be a 0, because 2 times minus 1 is minus 2, plus 2 is 0. 2 times 1 is 2, minus 2 is 0, and 2 times 1 is 2, plus 2 is 4. And then we just write down negative 1, 1, 1. Okay. Now, there is a column equivalent matrix. And now what we can do is choose either a row or a column, it doesn't really matter which, and see what you get. If I were doing it, I think I would go with the first row. Second column works quite well too, but I think I'll go with the first row. Okay? And we'll wipe out that. Now, this position here is a positive position, plus, minus, plus. Okay? So that's a minus 1 times the determinant of what's left down here, 12 minus 0. So that'll be times 12 equal minus 12. That is not equal to 0, therefore, howdy, it is invertible. Okay? So maybe not just by looking at it you can determine that, but by doing a matrix you can. All right, let me pause for a moment. Turn on my projector, swap my lights. Still raining, or? Yeah, it's raining. And I bet you the temperature is dropping like a rock, isn't it? My wife showed me on the weather map this morning before I left home the distinctions between the temperatures and stuff. And when I was driving to work, we live in Birmingham, it was 70, 72, something like that when I left home this morning. And I was driving in, I was listening to NPR radio, and they always give the temperature in Birmingham and then the temperature in Tuscaloosa. It was 70 in Birmingham, 50-something in Tuscaloosa. It was almost a 20-degree difference between those two cities that are not much more than an hour apart, or an hour and a half, something like that. And it was dropping. And as I drove this way, I could just watch the temperature fall, you know, still 70 behind me and still 50 ahead of me, and the temperature was dropping as I drove. I said, this is going to be a cold one before it's over with.
It wasn't that cold now.
Yeah. So by the time I leave at 8 o'clock tonight, it's going to be quite chilly. So I have on a short sleeve shirt, but I do have a jacket. But it's probably not going to be heavy enough jacket. But boy, at 70 degrees this morning, I just couldn't convince myself to put on a heavy coat. I probably should have. So anyway, let me go over the announcements. I think you've heard them before, but just in case. Our volleyball team is now in the NJCAA District L/M tournament. Okay, now the best I can figure, that stands for National Junior College Athletic Association. I don't know for sure. That's my guess. District, and I don't know if District L/M is just a district we're in here in Alabama, or if that's ladies and men. I don't know what that stands for, but the tournament is up in Boaz, Alabama, and that's Snead State Community College, I think, up there. And the tournament begins tomorrow. I don't know what time, but it'll be tomorrow, Saturday, and Sunday. So we wish the gals good success there. They're a great team, and we're looking forward to good things coming out of the tournament. All right, and the one other, I think I announced to you probably several times, the 1-week summer opportunity for college students interested in biopharma manufacturing careers. The students are paid $1,000 and travel expenses are covered for that 1 week. So that's a pretty good deal. I've got the website. I don't have any other information. All she says is the application deadline is in January. When in January, I do not know, but it's in January. But this website will take you to all the information you need, or at least take you to people who can give you that information. All right. We just did, or I just did, the top of page 122 on determinants and the inverse of a matrix. And the theorem was a square matrix is invertible if and only if, and that invertible also is another word for non-singular. If and only if the determinant of A is not equal to 0. If the determinant of A is 0, the matrix is singular, not invertible. Okay? If it is not equal to 0, then it is invertible, non-singular. Okay. Now, there's a little discovery block on the left-hand side of page 122. And it says use a software program or graphing utility to find A inverse of this matrix here. Now, this is a review from what we did in the last chapter. But let's do it. They say use a that would indicate to me it may be sort of hard to do, but I think we can do it. Here's matrix A. Okay? 6, 4, 1, 0, 2, 3, 1, 1, 2. Now, I'm not going to close out that matrix because what we're trying to find is its inverse. And we know how to do that. Okay? Remember, you adjoin this matrix with the identity matrix. 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay? Now, we do row reduction on this big matrix. Okay? What's the first thing we want to happen with that big matrix? 1 in the upper left. And the way you can do this is exchange these two rows. So row 1 and row 3 exchange. Okay? So this would produce, now we're not doing determinants now. If you did that with the determinants, you'd have to recognize that change your determinant by a sign. It would flip it from plus to minus. We're not worrying with determinants right now, even though that's this chapter. We're just doing row reduction. So that would become 1, 1, 2, 0, 0, 1. 0, 2, 3, 0, 1, 0, and 6, 4, 1, oops, yuck. Okay, 641 100. Okay, first step done. You got a 1 in the upper left. What's the next thing you want to happen? Zero's below. We got a 0 immediate below it, so we don't have to do a thing for that one. However, the 6 down there needs to become a 0. How will that happen? Negative 6 times row 1 plus row 3 is the new row 3. Okay, let's see if we can squeeze it in over here. Now this wouldn't change the determinant if you were keeping up with it at all, because you're just adding a multiple of one row to another row. So the top row stays the same, 1, 1, 2, 0, 0, 1. Second row stays the same, 0, 2, 3, 0, 1, 0. The new third row, though, is what? 0 for that one. Negative 2 for that one. Negative 11 for that one. I don't hear well, but I figured out what you said. And 1 for that one. 0 for that one. Negative 6 for this one. Okay. Now, what's the next thing you want to happen? You want a 1 to be the first non-zero element in the second row. Okay? Now, not very many good choices here. How you get that to happen is to divide this row or this row by 2 or negative 2. Okay? Now, I look at that and say doing that will produce a fraction here and here, so that's 2 fractions. Doing that down here will produce a fraction here and here. That will no longer be a fraction, but stop. So it's sort of pay your money and take your choice. I guess the numbers are smaller and easier up here, so let's divide that by 2. Okay. Well, actually, what I'm going to do first is add these 2 rows together to make this a 0 down here, because that's what I will want to happen. And then I'll divide that. Okay. I can cheat a little bit, but it's still legal in most states. Okay. So let's first row 2 plus row 3. That will make a 0 down there, which ultimately we're going to want. Okay, so row 1 stays the same, 1, 1, 2, 0, 0, 1. Row 2 for right, well, no, okay. Let's add them first and get the new row 3. 0, 0, negative 8, 1, 1, negative 6. Okay, now we're going to do row 2 divided by 2 is the new row 2. So what will it become? 0, 1, 3 halves, 0, 1 half, 0. All right. Now, what's the next thing we want to happen? The 0 above it. That's going to be fairly easy to do. What would we do? Negative row 2 plus row 1 is the new row 1. Okay? So it's just going to propagate those fractions, old boo hiss, but there's nothing we can do about it. So let's live with it. We're using row 2, so that's going to be 0, 1, 3 halves, 0, 1 half, 0. And let's just do the top row next. What would that become? 1, 0, negative 1 half, 0, negative 1 half, and 1. That's what you said, right? Yeah. All right, now what's the next thing we want to happen? Yeah, that leading digit down here in the third row, leading non-zero digit, we want to become a 1. How are we going to make that happen? And here's Charles. Okay. We're doing the discovery on the right-hand side of page 122. Okay? I can see now why they said use a graphing utility or something else, because you wind up with a bunch of fractions. But we can do it. What was the next thing we want to happen in this matrix here? Yes, divide row 3 divided by -8 is the new row 3. Okay, so that will produce 0, 0, 1, -1/8, -1/8, yuck. Okay. You said -3/4, right? No, +3/4, isn't it? Okay, I can't hear well. Okay, +3/4. All right. Well, we finally got the third row to be what we want it to, but we need to get the 2 rows above it to be, the 2 elements above that leading one to be a 0. So how are we going to make the first one? This one, first row. 1/2 row 3 plus row 1 is the new row 1. Okay? So 1/2 of 0, 0, whoops. I'm going to write down row 3. It's done. 0, 0, 1. -1/8, -1/8, +3/4. I hope I did that right. Okay? Next, row 1. What's it? 1, 0, 0. All right, that was the easy part. Okay, 1/2 of -1/8 is -1/16. Okay? Plus 0. Okay? 1/2 of -1/8 is -1/16 plus -4/16. Right? No, 8/16. So that would be -9/16, I believe, right? All right. -1/2 of, 1/2 of -1/8, that would be a -1/16 plus -4/16. That would, no, -8/16. I keep saying 4. -8/16 and -1/16 would be -9/16. I think that's right. If I say it anymore, I'm going to get it wrong. All right, and -1/2, 1/2 of 3/4 is 3/8 plus 4/8 would be 7/8. Agreed? Okay. Now, what do we do with row 2? -3/2, row 3 plus row 2 is the new 3/2. Or, row 3. Row 2, I can't talk. Literally, I can't talk. I don't know what's wrong with my throat. All right, so what does that give us? 0, 1, 0. All right, -3/2 of -1/8 is a +3/4. 3/16. Okay. And that's not added to anything, right? So it's 3/16, I think. Is that what you got? I don't know if this is a change of weather or what, but my head is clogging up on me like crazy.
Me too.
Is it?
Beat up right now.
Yeah.
Beat up.
Yeah.
I just came over something. It's like a battleship in my head.
All right. Negative 3/2 times negative 1/8 is again positive 3/16 plus 8/16 would be 8 and 3, 11/16. I'm having trouble doing math right now. Okay. And then minus 3/2 times 3/4, that would be a minus 9/8 plus 0 is minus 9/8. I see why they said use a graphing utility or a software program, because that's sort of a mess. Okay? I hope we got it right. Now, I was afraid they were going to say this. Says compare the determinant of A inverse with the determinant of A. Okay? Now, this is A inverse. We got to determine its determinant. Ew, yuck. Okay? We'll come down to that in a minute. Let's first do the determinant of A, where we started. All right, now, I think, what's that? Yeah, if we can, okay, I can't hear. Do what? Yeah, that's what I was just going to say. What either row or column operation would be good to do to try to create another 0 somewhere here? And there are a few possibilities, but I'd like them in one column or row. And what looks like it would be most likely is do a minus 6 of this plus that, which we ultimately did a little bit ago, but that will make that a 0, and then I think it will be easier to do. So let's do it. Is that one that you had in mind? Okay, so let's do minus 6 row 3 plus row, plus row 1. It's a new row 1. Okay, so we're leaving row 2 alone, 0, 2, 3, and leaving row 3 alone, 1, 1, 2. What's your new row 1? 0, negative 2, and okay, negative 11, wasn't it? Is that what you said? Yeah, negative 11. Okay. Made for some ugly numbers there, but now let's do a determinant. I wish I hadn't blocked those. Okay. And the determinant of that would be, let's eliminate this row and this column. That position is plus or minus. Down here. Plus, it's a plus position, so it's just going to be 1 times the determinant of what's left over. And what would that be? Negative 6 plus 22 be 1 times okay, what? Negative 6 plus 22. Isn't that 16? Yay or nay? Okay. All right. So that would be 16. There's the determinant of the easy one. Now let's do the determinant of the one that's not quite so easy. Okay. What's that? Yeah, this is not going to be particularly easy, but let's just pick a row or a column that we might be able to, or we can try doing our expansion, but that promises to be fairly big denominators pretty quickly. Now look here, and I can eliminate one of those very easily, okay? So what would it take to eliminate that? Okay? We need to multiply this by a six over wouldn't a 6 work? You multiply this by 6, you get 3/4, right? Okay. So I think that will be fairly easy to do. So let's first eliminate this one and then eliminate that one. Okay? With column operations, not row operations, column operations. Okay? This first one would be minus row 1. What is that coming in there? Minus row 1. Okay, plus row 2, no, I can't write, goodness gracious, minus column 1 plus column 2 is the new column 2, okay? So column 1 is minus 1/16, 3/16, minus 1/8. When you do the operation we just said, minus column 1 plus column 2. Well, minus 1/16 would be positive 1/16, minus 9/16 would be positive 8/16, which is 1/2. No, minus 1/2, right? Positive 1/16 plus negative 9/16 is negative 8/16. That's negative 1/2. That's not bad. Okay, let's do the next one. Minus 3/16 plus 11/16 would be 14/16. No, would be 8/16, which would be positive 1/2. Ooh, this is coming out better than I thought it would. And then minus 1/8, minus a minus 1/8 is positive 1/8 plus 1/8 is 0. All right, that was easy. Now we're going to do, didn't we say 6 times column 1 plus column 3 is the new column 3, right? So 6 times 1/16 is 6/16, which happens to be 3/8, right? That's a negative 3/8 plus 7/8 is 4/8, which is 1/2, right? This is coming out way easier than I thought it would. Okay? Then 6 times 3/16 would be 18/16. Okay, let's back off from that a minute. 6 times 3/16. The 6 will go into 16. 2 will go into both of those. Say again? Okay, yeah. So you would have, I'm going to scratch it down here because it's 3/16. Oh, 6 times that is, wait. Let me start over. Okay. Let's write it out. Okay. 6 times 3/16. Okay. 2 will go into that 3 times, 2 will go into that 8 times. So that gives 9/8 minus 9/8 is 0. Doesn't it? Okay. And then we do the same thing below, and you did 6 times negative 1/8 is negative 3/4 plus 3/4 is 0 there. So what we've just done is wound up with 2 choices here. You can either, even better than that. Remember, now this isn't quite right, but remember you can exchange rows and columns now. This basically, you can do this diagonal, and that gives you, because you have a lower triangular here. This isn't a upper triangular matrix because it's in the wrong quadrant. But since you can interchange rows and columns, it does produce the same thing. So this is going to be a minus 1/8 times 1/4 is minus 1/32. And that's not what I wanted it to be at all. I've made an error somewhere. And since they don't give answers here, I can't tell which. That was supposed to come out being, I think 1/16.
It's weird because, like, if you do it the regular way, it works.
What'd you say?
If you do it the regular way, I do negative 1/8 times the determinant of the Myers matrix.
Yeah.
You'll get negative 1/4. And then,
Right. Well, that's what we just did.
oh, my bad. Yeah.
I forgot. Yeah. You get the right sign because this is an up diagonal. You're right on that. That would give you a negative 1/8 times, and this is a positive position, so that's right. That would be a 0 minus a 1/4, so that's going to give you a 1/32. And it needs to be 1/16. So on one of these two, I made an error, and I don't know which one. But I'll tell you the conjecture. They come out being reciprocals with each other. Now, I bet you there's just so many places the error could have occurred. I'm not going to chase it down. I regret that I even did it. Okay, sorry about that. But that's what it would come out being. Let's move on to example 3. Sorry I wasted class time on that one. Okay? Yeah. Example 3's, if I'm not mistaken, was exactly the top of the page, isn't it? Which of the matrices has an inverse? We already answered that because we did them at the top. That was before you came in, Charles, where we found out that the first one, the A one, the column 2 was exactly a multiple of column 3. Multiple of minus 2. Minus 2 times column 3. Anytime you have that, determinant's going to be 0. And sure enough, it is. But the second one, and we did this in class, we came out with a minus 12, I remember, but I've erased it now, so I can't go back and reproduce it. Watch the first part of the class, and you'll see that. Now you get the theorem 3.8. And this is what I was just saying with that discovery. If A is an n by n matrix. Okay? Obviously, it has to be a square matrix, so you can't do a determinant. Okay? And it's not just an n by n matrix, it's an n by n invertible matrix. And what does that mean about its determinant? It's not 0. That's all we know. It can be anything. So since it's not 0, then here's the conclusion of that. The determinant of the inverse, if it is invertible, that means it has an inverse, and the determinant of the inverse is exactly 1 over the determinant of A. That's what the conjecture was showing. We botched it doing something in the calculation there. We came close, but not quite close enough, and that gave us this. We should have had a 1/16 rather than a 1/32. So we're off by 2 somewhere. All right. So let's move on to example 4. It says find the determinant of the inverse of A given what A is. So here's A. It's 103, 0, negative 1, 2, and 2, 1, 0. Okay? It says find the determinant of the inverse. Hey, notice, we don't care what the determinant, what the inverse is. We just want to know what the determinant is. So do you need to do row reduction here? No, all we need to do is find the determinant of A, and then we know the determinant of its inverse. What is that? The reciprocal. Now, this one, I can almost guarantee you, is going to work out far better if you just expand it. Okay? So let's do that. Repeat the first 2 columns, 1, 0, 2, and 0, minus 1, 1. Now do our diagonals. Why did I say it's going to be better this way? You got zeros all over this thing, okay? So this will be 0. This will be 0. That would be, hey, I can do those all right. Those add to 0. Now do the, let me erase these so you can see better. Okay, now let's do our up diagonals. And what's true about the up diagonals? The opposite of it. Okay, so this will be, and that one happens to be second. I can't hear you. You're probably saying it.
He said he got it right. He said
What?
6.
6. Okay, that's 6. And then this one would be
2.
minus 2.
Minus.
And so that's equal to 4. That's all we got to do. Oh, wait, yeah. No, we got one more. Plus 0. Okay? So this gives us 4. There's the determinant of A is equal to 4. So what's the determinant of A inverse? I don't care what A inverse is. I just want to know what its determinant is. 1/4. That's a lot easier than taking the inverse of that matrix, you know, doing a row reduction with the augmented thing, and then once you got that, then doing its determinant. Please no. Be lazy. Find the easy way to do it, okay? And you got it. And sure enough, it is 1/4. Now, I don't know if you remember this, but we started quite a while back and then added and added and added to equivalent conditions for a non-singular matrix. So we're going to start with the ones we had before and now add this new one that we have. So here's what it is. If A is an n by n matrix, that means a square matrix, then the following statements are equivalent. Okay, number 1. A is invertible. Okay, now, it's not saying every n by n matrix is invertible. It's just saying if A is a square matrix, then the following statements are equivalent. So basically, this one's saying, let's assume A is invertible. If A is invertible, then all of these are true. First, and this is one from way back, A times X equal B has a unique solution for every n by 1 column matrix B. Or you could call it a column vector B. Okay? For every one. There's, without fail, whatever column matrix or vector you put there, B, you can find a different unique solution. Okay? Number 3, I can't count. Okay? AX equals 0. Now that should have been a bold 0. Okay? A vector 0 has only the trivial solution. Okay? Which means, and it basically comes right from there. For every choice of B, and if B is all zeros, then the X, the only one that works, is all zeros. Because you know all zeros will work. And this says that it has a unique solution. So if all zeros work, that's the only one it's got. None others will. Okay? So there's number 3. We did all these before. Number 4. A is row equivalent to I sub n. Yeah, that's how we found. If A is invertible, it has to be row equivalent to the inverse to the identity matrix I, because if it's invertible, you can reduce it and you wind up with that. Okay? So that's true. Okay? Number 5, which I think we did in the last section or chapter or somewhere we did, A can be written as a product of elementary matrices. A can be written as a product of elementary matrices. We did that last time, sometime. Now the new one that we've added to it, if A is invertible, the determinant of A is what? Not equal to 0. Okay? Not equal to 0. It can be anything else in the world. Negative 0.0000001. That's not equal to 0 is fine. Okay? It's invertible then. But if that determinant is 0, not invertible. Then none of these other things are true. All right. Let's move on to example 5, bottom of page 123. Which of the systems has a unique solution? 2x squared minus x, 2x sub 2 minus x sub 3 is equal to minus 1. 3x sub 1 minus 2x sub 2 plus x sub 3 is equal to 4. 3x sub 1 plus 2x sub 2 minus x sub 3 is equal to minus 4. Or B, which is 2x sub 2 minus x sub 3 is equal to minus 1. 3x sub 1 minus 2x sub 2 plus x sub 3 is equal to 4. And 3x sub 1 plus 2x sub 2 plus x sub 3 is equal to minus 4. which of these systems has a unique solution? Can you look at that and tell? I'm going to cheat a little on it.
Probably the second.
The second one does. Any reason why? All right. What? What? Say this again.
The last row of the second one, compared to the last row of the first one, the signs are different. In particular,
Okay.
it's 2x squared minus x3 on the first one, but it's 2x squared plus x3 on the second one. So your answer is going to come out to be minus. That's compared.
Okay. Your type of reasoning is pretty good. However, I don't think what you're saying, what I think I hear you saying, if you were to add these two rows together, you get 6x of 1 is equal to 0. Well, that's okay. X of 1 can be 0. There's nothing wrong with that. Okay? Now, here's what you should be doing, and I think the author was really lazy here, but maybe it was on purpose. Look at the coefficient matrix. 0, 2, minus 1, 3, negative 2, 1, 3, 2, minus 1. And then look back at the page just before this. At the top of the page and at the bottom of the page. Didn't I just describe this here? 0, 2, minus 1, 3, negative 2, 1, 3, 2, minus 1. That's that matrix. And we've already done, I did it once, but it was on the page twice, that because, look at the coefficients. Multiply these coefficients, minus 1, 1, minus 1, by minus 2, and you get 2 minus 2. These two columns are multiples of each other, okay? The coefficients are. Now, you don't use that when you're solving equations, but because it is, that makes the determinant 0. That means that determinant is 0, okay? This one, however, you can't do that, and we did go back and do the determinant of this, and when we did it, we found out it was 12, if I'm not mistaken. They did it at the bottom of the page too. Oh, negative 12, not 12, minus 12. But that's not 0. So that means it does have a unique solution. Now, did they ask for what is the unique solution? No. But we know it has a unique solution. So which of the systems has a unique solution? And like you said, it's the second one. And the reason is because we'd already done that with its coefficient matrix and found out that does have a non-zero determinant. Okay? And that's all you need to know. That's the only question they asked, which of them has a unique solution. They didn't ask what that solution was. Okay. Now, how are we doing on time? Oh, we got some time. Now let's go to page 124. Are the questions on 123? Did y'all see why that's true? Okay. Page 124, determinants and the transpose of a matrix. Okay? I think I'll clean the slide here. All right. The next theorem tells you that the determinant of a transpose of a matrix is equal to the determinant of the original matrix. Okay? So basically what it says, if A is a square matrix, they say it different ways, but that's what they mean, square matrix, then, okay, the determinant of A is equal to the determinant of, I can't write, the transpose of A. Okay? What I wanted to keep disappeared and what I wanted to get rid of stayed. Okay. All right, that's all there is. Now, they don't prove it, but if you think about it very carefully, okay, if you're exchanging rows and columns, that's what a transpose does, okay, then the minors, just in a different order, are all the same. The cofactors are all the same. So therefore the determinants have to be the same. Okay? Now it wasn't approved, but it was. So they're going to ask us to show this for a matrix here. And they are being very, very kind to you. Don't expect it on the test. No, I didn't say that out loud, did I? Okay? Here's matrix A. No kindness on tests, okay? 3, 1, negative 2, 2, 0, 0. See where the kindness came in? Okay. And negative 4, negative 1, 5. That's matrix A. All right? What you want to do first? Find its determinant or find its transpose? Second? Determinant. Let's do the determinant. So what's the determinant of A? What position would you choose? Always look for the row or column with the most zeros, and that's the second row, okay? And the non-zero entry there is in the first column, so we'll wipe out that too. Now, the question you ask yourself, what's the sign of that position? That would be negative. So negative 2, and then we do the determinant of what's left. That's 5 minus 2 is 3. So the determinant of that matrix is negative 6. Now let's do the transpose of that matrix. What would be a transpose? You tell me. You tell me. What's the transpose of that matrix? Remember how we do transposes? Second? Okay, he's doing the first row. 3, 2, negative 4, right? Next. 1, 0, negative 1. Negative 2, 0, 5. Is that what I heard? Okay, good. Now, if you're doing the determinant of that transpose, what would that be? What would you choose? I would use the second column. That's got the most zeros in it, right? And then, because the non-zero entry is up there, let's do that one. What's the sign of that position? Negative. That would be negative 2 times, cross product here would be 5 minus 2. This would be negative 2 times 3 equals negative 6. Like I said, the minors and the cofactors and everything are identical. Okay? You just change rows and column and choose the same column corresponding to the same row you did before, because that's the easy one to do. Everything stays the same. So sure enough, the determinant of a matrix is the determinant of that transpose of that matrix. Does this require the matrix to be invertible? No. But if it's not invertible, what's the determinant? 0, and the other one would be 0. So it's still no sweat. And sure enough, we got it right. Now there is a linear algebra applied at the bottom of the page, and that deals with Laplace transforms. Now, we haven't hit the name Laplace before, so there's a potential paper topic. Hint, hint, okay? And here's a Laplace transform. You can talk about how they did it, how they developed, how Laplace came up with them, or who in the world uses them anyway. And they show here,
Don't electrical engineers use that?
big time. Electrical engineers use Laplace transforms a whole lot, okay? I'm not saying other engineers don't, but electrical definitely do. And what they're talking about here is engineering and control theory, and I think that's like the PLC controllers and those kinds of things. I think that's redundant, but I think they use Laplace transforms a lot in those. So, several potential paper topics if that's of any interest. So homework exercises 3.3 would include any of the odds 1 through 5. They're all at Calc Chat. Any of the odds 7 through 11. They're all at Calc Chat. 13 or 15. They're both at Calc Chat. Any of the odds 17 to 23. They're all at Calc Chat. 25 through 29. They're at Calc Chat. 31 to 35. They're at Calc Chat. 37 to 43, they're at Calc Chat. 45 to 49, they're at Calc Chat. Yeah, I'd say 45 to 49, yeah, Calc Chat. 51's at Calc Chat. Yeah. 53 or 55 is at Calc Chat. 57 is a proof. It should be at Calc Chat. 59 or 61 should be at Calc Chat. 63 is a guided proof. It should be at Calc Chat. 65 is a true-false. It should be at Calc Chat. There is a writing exercise 67. I don't know if that's a Calc Chat or not, but you can look. 69 is a proof. Now here comes another definition in the problem set which sort of irritates me, okay? If it's worth being a definition, put it in the text, not in the problem set. But anyway, they're defining what orthogonal matrices are. And says here in these exercises 71 to 75, determine whether a matrix is orthogonal. Then they give you the definition of orthogonal. An invertible matrix of an invertible square matrix A is orthogonal if its inverse is equal to its transpose. Okay? So that's the definition there. That should have been, in my mind, in the text. So you can check these out to determine which of these square matrices are invertible. All right, then 79 should be at Calc Chat, and 81's a proof should be at Calc Chat. Goodness, I'm running out of steam so fast. Part of it is not being able to breathe. The other part is I'm so hungry I can't think. But let's move on. We don't have much more time, so let's get done what we can. Section 3.4 are applications of determinants. Okay, now, the first word here, you kind of heard something similar to it, but it's not quite the same. We talked about adjoining one matrix to another, like adjoining the identity matrix to a square matrix of the same size, and then we're going to do row reductions and come up with the inverse to see if it has an inverse. That's adjoining one matrix to another. This is talking about the adjoint of a matrix, which is a little bit different, okay? And it's kind of a pain in the neck type thing to do, Okay? So far in this chapter, you've studied procedures for evaluating properties of determinants. In this section, you'll study an explicit formula for the inverse of a non-singular matrix and use that formula to derive an inverse theorem known as Cramer's rule, which we solved, I think, in 3.1, or came up with in 3.1. And then you'll solve several applications with determinants. Now, we're not going to do them all. We may do a couple. Okay. Now, if you remember back from section 3.1 that the cofactor Cij of a square matrix A is defined as the sign, okay, of the position times the determinant of the minor of that position, okay? The sign of the position, onto the minor of the position, the determinant of that minor, okay? So, once you come up with a matrix of, okay, what you do, you start with a matrix, square matrix, n by n, okay? You determine the n rows and n columns made up of the cofactors of that matrix. Okay? That's a pain in the neck, but you do it. Okay? Then you transpose that matrix, and that's what you call the adjoint of A. Okay? So, let's do that with a matrix. Okay? First, you come up with another matrix, which is a matrix of cofactors. Then you transpose that matrix. That gives you the adjoint of A. So let's start with matrix A. I don't know if we'll be able to get all this done, but let's try. A, 3 by 3. -1, 3, 2. 0, -2, 1. 1, 0, -2. All right. Now, first thing we've got to do is come up with another square matrix called, okay, and it doesn't have a name, but it's the matrix of the cofactors of this matrix. All right. So what this means, folks, is for this position right here, the 1, 1 position, you first decide the sign of that position. What's the sign of that position? No, the sign of the position is positive. The sign of the element is negative. The sign of this, remember, it's plus, minus, plus, minus, plus, minus, plus, minus, plus. Okay? The sign of this position is plus. Okay? Now, as I said here, the cofactor Cij of a square matrix is defined as the sign, which I just determined was positive, times the determinant of the matrix obtained by deleting the ith row and the jth column. So you eliminate that row and that column and take the determinant of this. And that would be -2 times -2.
Oh, it's positive 4.
Positive 4 minus 0. So that would be 4. The sign was positive, so the cofactor is 4. Okay? You do that with every position. Okay? All right. Let's go to this one. What's the sign of that position? Negative. Okay? So hang on to that. Okay, let's wipe out that row and that column and take the determinant of this. That would be 0. Yeah, but since it's on the upswing, that's -1, right? And that was a minus, so that would be a +1, right? So there's a 1. All right, let's do this position. Okay, what's the sign of that position? Positive. Plus minus what? Okay, positive. Okay, now wipe out that row in the right column. What's the determinant of what's left?
4.
Where'd you get a 4?
2 times. Where we at?
You do this on 0
0.
minus this.
2.
2. Okay, that gives you a 2. Okay. All right. Now let's take this one. Okay. Now just because that's a 0, it doesn't matter. We're just looking for the cofactor. The cofactor is the sign of this position. What's the sign of that position? Plus, minus. Always start with a plus here and go right or left, up or down, and change sign every time. Don't do diagonals, right or left. Plus, minus. That's a minus. Okay? So wipe out this. I can't do it without covering too much. Wipe out this and that. So what you have left is, no, wipe that out. I don't want to cover it.
3. It's going to be 0. Wait a minute, I'm sorry. 6.
Negative 6.
Negative 6.
Okay, negative 6 minus 0. So that's negative 6. But that was a?
0.
No.
Oh.
The sign.
Minus.
Minus. So that would be a plus 6 then, right? Yeah, okay. I'll make sure the book got it right. Okay? So let's go to the middle position. What's the sign of that position?
Minus.
Positive. Okay, sign of that position, positive. Now wipe out this middle row and middle column, so you're just using the corners.
That's how we do it. 0.
Yeah, it comes out 0. This would be 2 minus 2 is 0. Okay, good. I'm sorry, I can't hear. Okay. Exactly. All right. Now let's do this position. What's the sign of that position?
Minus.
Minus. Okay. Wipe out that column and that row. And what do you have left?
It's going to be 3.
Negative 3, you said?
No, 3.
3. Because this would be negative, but that's a negative position, so that gives you 3. Perfect. Okay? Now, let's come down here to this one. What's the sign of that position?
Plus.
Positive? Yes. Okay. Wipe out that row and that column, and what do you have left?
That's going to bring us to 7.
7, exactly. And it's a positive position, so that would be a 7. Positive 7. Okay? Now let's go to this one. What's the sign of this position?
Plus.
Plus, minus, plus, minus, plus, minus, plus, minus. Okay? Anything on the diagonal is plus, so you can start here. Plus, minus. Okay? It's minus, no matter how you get there. Okay? Now, wipe out the middle row, the middle column, and the bottom row. Okay? And what you got left?
1.
1. Okay, because it's a minus 1, and its minus position is a plus 1. So that's a 1. Okay? And then this last one. What's the sign of that position?
Minus.
Okay? Everything on the diagonal is positive. Okay? Because the diagonal, 1, 1, 2, 2, 3, 3, add those together, that's always even. Okay? So that's always positive. Okay? So the position is positive. So wipe out this row of that column, and what you got?
It's going to be positive
2. You got it. Okay. There's the matrix of cofactors. Okay? Now, we do the transpose of that Okay? And what would that be? 467 101 232. That is now the adjoint of A. Okay? I was trying to see if they have a shorthand notation for it. They do not. I was hoping they did. It's the adjoint of A. That's what it is. Doesn't look anything like A. It's not. But it was derived from A. First do the cofactors, the matrix of the cofactors, then transpose that. That gives you the adjoint of A. Why in the world would we mess with that? Well, to run ourselves out of time. That's why we did. Okay. So we've got that. We've done that one. We'll start at the top of the next page Tuesday, next week. Now, I do have a question for you. Okay? And that question is this. Would you like the Chapter 3 test, because this is the last section in Chapter 3, so you can have the weekend to start working on it. It's not due. It won't be due anytime soon. It'll be 1 week from when we finish. So I'll tell you right now, you can do 1, 2, 3, 4, 5, 6, 7, 8. I think you can do everything except maybe number 10. You don't have to do that many, but you want to get started on it now, over the weekend, or you want to wait and get it on Tuesday to finish the section? On it now?
Yes, sir.
That one back. My work study student this morning, my master, I had some of the, oh, wait. There's 2 pages. I've got it. You get page which. Well, y'all want to figure it out.
Yeah, I think the second page, 6.
Yeah, make sure you don't have 2 copies of the same page. Okay. So y'all can start working on those. I thought we might get a little further than we did today, but this was the hard part, because doing those. Now,
This is test 2.
it says test 2, but it's test 3. I forgot to change the title. I didn't even notice it until I ran it off. I said, what? Okay. You can write 3 in there if you want to. We've just got page 129, 130, 131. Ooh, we got longer than I thought. So it probably won't be due for another week or 2. Okay. At least a couple weeks. Because we've got a lot, but you can do most of it now so you can get started on it early. If you choose. You don't have to, but you can if you want to. Good deal. Any questions? All right. Have a good weekend. We'll see you Tuesday. Stay warm. It's supposed to be pretty cold this weekend.
Yes, sir.